use Green's theorem to find the area of the ellipse x squared divided by a squared plus y squared divided by b squared equals 1. According to the Green's theorem, we know that we can evaluate a line integral of a given vector field over a closed curve C by calculating a double integral over the region D bounded by the same curve, and vice versa. Of course, we require the condition that the curve C is simple, closed, and then piecewise smooth, and also being oriented counterclockwise. And in solving this question, we will be applying the Green's theorem in a reverse direction. So we will be treating the boundary of this ellipse as our closed curve C, and then the interior of this ellipse is going to be treated as the region bounded by the curve, which is the region D. Okay, and then we're gonna write out the area of the ellipse. Area of ellipse can be expressed as a double integral of the function 1 dA, where this region D represents the interior of this ellipse. Okay, and then our idea is that we want to construct two functions p and q such that partial q partial x minus partial p partial y equals exactly 1, so that we can replace this 1 with this expression, and then we will be applying the Green's theorem to change that into an expression of line integral, so that we can find the area by finding this line integral. Okay, so now let's try to construct these two functions. Notice that the choice of these two functions is not unique. You can come up with many different setup p and q, as long as partial p partial q partial x minus partial p partial y equals 1. For example, I can come up with one of the easiest set of these two functions by letting q equal to x and p equal to 0. Okay, we then can calculate partial q partial x is going to be 1, right? And then partial p partial y is going to be 0. So this is going to be 1 minus 0, which equals 1. And that is a construction of p and q. After we have chosen the function p and q, we then can replace this 1 with this expression. So then we can write double integral of partial q partial x minus partial p partial y dA. And then according to the Green's theorem, this expression can be changed to this one, and that is going to be the line integral of the curve p dx plus q dy. We then take a look at our curve, which is the boundary of this ellipse. We have the parametric equation of this ellipse, which is x equal to a cos t, y equal to sine t, where t ranges from 0 to 2 pi. And this parametric equation, this parameterization, tells us that this curve is going counterclockwise as t ranges from 0 and 2 pi. So it satisfies what is required in a theorem. Okay? Now let's try to find this line integral. We know that p is equal to 0, right? So this part is going to disappear. And then q is our x, and then we can replace x with a cos t. Okay, so this is going to be like integral from 0 to 2 pi. And then our q is going to be a cos t, right? And then we're going to write out dy. What is this dy? To find this dy, we're going to take a look at this. Y equal to b sine t. So we know that dy is going to be b cos t dt by differentiating this with respect to t. Okay, so there's going to be b cos t dt. Now the rest of the work is just to find this integration. So that is ab from 0 to 2 pi cos square t dt, which can be written as cos 2t plus 1 divided by 2 by using trig identity. Okay? And then we're going to find the antiderivative of this and apply the fundamental theorem. We then have this being sine 2t plus 1 over 2t with upper bound 2 pi and 0. Okay? And then that's going to be AB times pi. Okay?